Every second of the universe's existence, every collision of galaxies, every whisper of a dying star, every moment since the Big Bang might still be out there, etched into the fabric of space itself. Think about that for a second. We're not just talking about light traveling across the cosmos, showing us the past through telescopes. No, this is something far stranger. What if space isn't empty at all, but a vast, dynamic library, silently recording everything that's ever happened? That's the jaw-dropping idea at the heart of cosmic memory, the notion that space-time itself might be storing the universe's history in ways we're only beginning to understand. Picture this: you're walking through a forest, and every step you take leaves behind an invisible imprint, a kind of ghostly footprint that never fades. Now imagine the universe doing the same thing, but on a scale so immense it defies comprehension. Einstein showed us that massive objects bend spacetime like a heavy ball on a trampoline. But what if those bends don't just smooth out over time? What if they linger, preserving the echoes of ancient cosmic events? Gravitational waves, ripples in spacetime from black holes colliding, are just the beginning. Scientists now suspect that quantum entanglement, black holes, even the afterglow of the Big Bang, might all be part of a grand cosmic archive, a hidden ledger of everything that's ever been. This isn't science fiction. It's the cutting edge of physics, where mind-bending theories collide with real-world discoveries. Over the next few minutes, we'll explore how spacetime could be the ultimate time capsule, from the holographic principles claim that our 3D universe is a projection of data stored on a 2D boundary, to the eerie possibility that black holes aren't just destroyers, they're cosmic librarians, safeguarding information in ways we can't yet fathom. By the end, you'll never look at the night sky the same way again, because if these theories are right, the universe isn't just expanding, it's remembering. And we're on the verge of learning how to read its story. So, are you ready to dive into the architecture of cosmic memory? Let's begin. When we say the universe has a memory, we're not talking about something as fleeting as human recollection. This isn't about fading impressions or forgotten moments. It's about the very fabric of reality, holding onto its past in ways that defy ordinary intuition. Think of spacetime not as a blank canvas but as a dynamic, ever-changing sculpture, where every event leaves a permanent mark, no matter how small. Einstein's theory of relativity gave us the first clues. Massive objects like stars and galaxies don't just sit in space, they bend it, warping the geometry of spacetime itself. And here's the mind-blowing part: those warps don't just vanish. They linger like fingerprints pressed into cosmic clay, preserving the echoes of collisions, explosions, and movements that happened billions of years ago. But relativity is only half the story. Quantum physics adds another layer to this cosmic record-keeping. Particles that become entangled, linked in such a way that the state of one instantly influences the other. No matter how far apart they are, seem to carry a shared history, a kind of quantum handshake that persists across the universe. Some scientists believe these entangled states could be threads in a vast, invisible tapestry, weaving together events that happened light years apart. Imagine two particles born in the fiery chaos of the early universe, still whispering secrets to each other across billions of years. That's the scale of cosmic memory we're dealing with. So what does this mean for us? If spacetime is indeed a vast archive, then every event, from the birth of a star to the collision of black holes, might be encoded in its structure. Gravitational waves, ripples in spacetime detected by observatories like LIGO, are like the universe's way of replaying its greatest hits. But what about subtler imprints? Could the faint distortions left by ancient supernova or the quantum entanglement patterns from the Big Bang still be hiding in plain sight? The answer might lie in the way we read these cosmic records. Just as archaeologists piece together history from fragments of pottery, physicists are developing tools to decode spacetime's hidden messages, whether through gravitational wave astronomy, quantum experiments, or even simulations of the early universe. The implications are staggering. If we can learn to interpret these cosmic imprints, we might uncover chapters of the universe's history that were thought lost forever. Did the universe undergo phases we can't yet imagine? Are there echoes of events predating the Big Bang itself? The idea that space itself could be a silent witness, preserving the past in its very geometry, turns the cosmos into something far more intimate, a living, breathing chronicle of time. And the most exciting part, we're only just beginning to learn how to read it. Einstein didn't just change how we think about gravity. He gave us a new way to see space and time as something alive, dynamic, almost breathing. His theory of general relativity revealed that spacetime isn't a static stage where cosmic events play out. Instead, it's more like a stretchy, malleable fabric, reacting to every tug and push from matter and energy. But here's the twist: those reactions aren't fleeting. When a star explodes or black holes collide, the distortions they create in spacetime don't just vanish. They linger like ripples circling outward in a pond long after the stone has sunk. These ripples are gravitational waves, the universe's way of whispering its secrets across billions of years. The detection of gravitational waves in 2015 was a watershed moment, not just because it confirmed Einstein's century-old prediction, but because it proved spacetime has a kind of memory. Those waves, born from cataclysmic events like black hole mergers, traveled unimpeded through the cosmos, carrying precise details about their origins. It's as if spacetime itself etched a record of those collisions into its very structure, preserving their energy, their spin, even their final moments. But if violent events leave such clear imprints, what about quieter ones? Could the gentle drift of galaxies, the slow dance of cosmic filaments, or even the birth of stars also leave faint but detectable marks? Some scientists speculate that spacetime might be riddled with subtler distortions, ancient wrinkles from events so old, their light has long since faded from view. Imagine running your fingers over an old vinyl record. Even if the music has stopped, the grooves still hold the song. In the same way, spacetime's geometry might encode a soundtrack of the universe's history, from the faint hum of primordial quantum fluctuations to the thunderous crashes of galactic collisions. The challenge: learning to play those grooves. Current gravitational wave detectors like LIGO are tuned to catch the loudest cosmic crashes, but future technologies more sensitive, more precise might one day pick up the faintest murmurs, the whispers of events that predate stars themselves. This idea flips our understanding of the cosmos. We're used to thinking of the past as something lost, visible only in the distant light of galaxies or the fossilized remnants of dead stars. But if spacetime itself is a recording medium, then the past isn't gone. It's folded into the universe's very architecture, waiting to be decoded. Every planet, every black hole, every ripple in the quantum vacuum might be part of an immense, interconnected ledger, a cosmic chronicle written not in ink, but in the curvature of reality. And if that's true, then the universe isn't just expanding, it's remembering. The question is, how much of that memory can we learn to read? Quantum entanglement feels like something ripped straight from science fiction: two particles, separated by vast distances, instantaneously influencing each other's states as if they're still touching. This bizarre phenomenon, which Einstein famously called spooky action at a distance, isn't just a quirk of quantum mechanics. It might be the universe's way of keeping a hidden ledger, a cosmic accounting system where every interaction leaves an indelible mark. Imagine two photons created together in the heart of a dying star. Even if one ends up on the far side of the galaxy, measuring its partner's spin here on Earth would instantly reveal its counterpart state, as if no time or space had passed between them. This eerie connection suggests that entanglement isn't just a fleeting bond, it's a permanent record of their shared past, a quantum handshake that never lets go. But here's where it gets even stranger. Some physicists argue that entanglement isn't limited to pairs of particles. The entire universe could be crisscrossed by a vast, invisible web of entangled connections, a network so intricate it encodes the history of everything. Picture the early cosmos, a seething plasma of particles born in the Big Bang's aftermath. As those particles sped apart, their entanglements didn't sever, they stretched, weaving a tapestry of correlations that might still exist today. If we could map these quantum threads, we might uncover fingerprints of the universe's infancy, like archaeologists deciphering ancient hieroglyphs etched into the fabric of reality itself. The implications are staggering. Entanglement could preserve details about conditions we thought were lost forever. The temperature fluctuations of the primordial fireball, the density variations that seeded galaxies, even hints of what came before the Big Bang. Experiments with quantum computers are already teasing apart these connections, simulating how entangled states might retain information across cosmic timescales. It's as if the universe left us a puzzle where every piece is a particle, and the way they fit together tells a story older than time. Yet the most tantalizing idea is this: if entanglement truly forms a cosmic ledger, then space itself might be less like empty void and more like a vast hard drive, storing data in the quantum links between particles. Black holes, gravitational waves, even the afterglow of the Big Bang could all be part of this interconnected system, each event adding another entry to the universe's grand chronicle. The challenge: learning to read it. Just as Rosetta Stone unlocked ancient languages, future breakthroughs in quantum physics might give us the key to decoding spacetime's deepest memories and rewriting our understanding of history itself. Black holes have long been painted as the ultimate cosmic villains, consuming everything in their path, crushing matter into oblivion, and erasing information from the universe. But what if we've misunderstood them entirely? Instead of cosmic shredders, black holes might actually be the universe's most meticulous librarians, preserving every scrap of information that falls into their grasp. This mind-bending idea comes from the holographic principle, a theory suggesting that all the data swallowed by a black hole isn't destroyed but is instead imprinted onto its event horizon, the point of no return. Picture it like a cosmic fingerprint. Every star, planet, or speck of dust that crosses that boundary leaves a trace, encoded in the fabric of spacetime itself. Stephen Hawking's groundbreaking work on Hawking radiation adds another layer to this mystery. He showed that black holes aren't entirely black, they slowly emit radiation, losing mass over time until they eventually evaporate. But here's the twist: that radiation isn't random noise. It might carry subtle imprints of the information that fell in, like a faint echo of the black hole's past meals. This means that even as a black hole fades away, it could be quietly whispering its secrets back into the universe, preserving a record of everything it ever consumed. The implications are staggering. If black holes store information on their surfaces and leak it back out via Hawking radiation, they're not just passive traps, they're active participants in cosmic memory. Imagine a black hole as a celestial hard drive, its event horizon etched with the history of every object it's ever absorbed. over billions of years, that data could slowly re-emerge, like pages from a cosmic diary being carefully unspooled. This challenges everything we thought we knew about information loss and the nature of reality itself. But how could something as chaotic as a black hole preserve order? The answer might lie in quantum mechanics. At the smallest scales, particles and their interactions are governed by precise rules, and information, whether it's the spin of an electron or the composition of a star, can't just vanish. The holographic principle suggests that the 3D chaos inside a black hole is perfectly mirrored on its 2D surface, like a hologram projecting a complex image from a flat sheet. This means the messy collapse of matter inside the black hole is translated into an orderly pattern on its horizon, a kind of cosmic barcode that retains every detail. What's even wilder is that this idea might extend beyond black holes. Some physicists speculate that the entire universe could operate like a hologram, with all the information about our 3D reality stored on a distant 2D boundary. If true, black holes are just the most extreme example of a universal rule. Nothing is ever truly lost. The past isn't erased, it's archived, waiting for us to learn the language to read it. So the next time you picture a black hole, don't think of it as a cosmic trash compactor. Think of it as a vault, a celestial historian meticulously recording the universe's story in a language we're only beginning to decipher. And if we can crack that code, we might unlock chapters of cosmic history we never dreamed were still within reach. The holographic universe theory turns everything we think we know about reality on its head. Imagine your entire life, every sight, sound, and sensation existing not as a three-dimensional experience, but as data painted onto a flat, distant surface like a cosmic projector screen. This isn't just wild speculation, it's a serious scientific hypothesis born from the study of black holes. When physicists realized the information swallowed by a black hole might be encoded on its two-dimensional event horizon, they asked a revolutionary question: what if our universe works the same way? That all the stars, galaxies, and even the chair you're sitting on are just holographic projections from a thin, shimmering layer at the edge of existence. At first glance, the idea seems absurd. How could the rich, textured world around us, the depth of a forest, the curve of a mountain, be reduced to flickering patterns on a flat canvas? But think about how a credit card hologram works. Tilt it in your hand, and suddenly a three-dimensional eagle seems to leap off the plastic. Now scale that up to universal proportions. The holographic principle suggests that the boundary of our cosmos acts like that credit card, encoding all the information needed to generate the illusion of depth, time, and even consciousness itself. Every supernova explosion, every whispered conversation, every heartbeat across cosmic history might exist as intricate ripples on this unimaginably vast two-dimensional surface. What makes this theory so compelling is how it solves one of physics' biggest puzzles: the nature of information. In classical physics, information can't be destroyed, it just changes form. But black holes seem to violate this rule, swallowing matter and erasing its details. The holographic principle neatly resolves this paradox. Nothing is ever truly lost. It's just transferred to the universe's hard drive, that distant two-dimensional boundary where data is stored with perfect fidelity. This implies that time and space aren't fundamental features of reality but emergent properties, like the illusion of movement in a flipbook. The implications for cosmic memory are staggering. If the holographic principle holds, then the universe's entire history isn't just preserved, it's actively playing out right now on that boundary layer. The moment of the Big Bang, the formation of the first stars, even your childhood memories could all exist as frozen snapshots in this cosmic archive. Some theorists go further, suggesting that if we could decode this hologram, we might access events outside our observable universe or even glimpse multiple timelines branching from quantum decisions. Critics argue that the holographic principle stretches our understanding of physics to the breaking point. After all, how could a two-dimensional surface contain the complexity of human thought or the vastness of galaxy clusters? But supporters counter with a surprising fact: the math checks out. The equations describing quantum gravity, the elusive theory bridging Einstein's relativity with quantum mechanics, align eerily well with holographic models. It's as if the universe left us a clue, hinting that reality is far stranger than we ever imagined. Whether the holographic principle ultimately proves true or not, it forces us to rethink what memory really means. If the past isn't gone but imprinted on the fabric of the cosmos, then time itself might be an illusion, a side effect of how we perceive this grand projection. The next time you look up at the night sky, consider this. Those twinkling stars might not be distant objects at all, but pixels in a cosmic display, their light just the faint glow of data being read from the universe's ultimate storage device. And if that's the case, then decoding the hologram could be the key to unlocking the deepest mysteries of existence itself. The cosmic microwave background is more than just ancient light. It's the universe's first baby picture, a faded but priceless snapshot taken when the cosmos was a mere 380,000 years old. Back then, the universe wasn't the vast, star-studded expanse we see today. It was a seething, opaque soup of particles, so dense that light couldn't travel more than a hair's breadth before being absorbed. But as the cosmos expanded and cooled, something extraordinary happened. Atoms formed, and suddenly, light could race freely through space. That first burst of liberated photons is what we now detect as the CMB, a faint glow filling every corner of the sky, its wavelength stretched by 13.8 billion years of cosmic expansion until they've faded into the microwave range. What makes this glow so remarkable isn't just its age, but the story it tells. If you could see the CMB with your eyes, it would look like a nearly uniform blanket of light. But hidden within that uniformity are tiny fluctuations, hot and cold spots no larger than 1/100th of a degree. These imperfections might seem insignificant, but they're cosmic gold. They're the fingerprints of quantum fluctuations from the universe's earliest moments, stretched to astronomical scales during the rapid inflation period. Like ripples frozen in time, they reveal the density variations that would later grow into galaxies, clusters, and the vast cosmic web we see today. Scientists study these patterns with the precision of detectives reconstructing a crime scene. Space telescopes like Planck and WMAP have mapped the CMB in exquisite detail, transforming those subtle temperature differences into a treasure trove of data. The hotspots, those are regions where matter was slightly denser, the seeds of future galaxy clusters. The cold spots, areas where matter was thinner, destined to become the voids between cosmic structures. But the CMB's secrets go even deeper. By analyzing the polarization of this light, the direction its waves vibrate, researchers can glimpse the universe's very first moments. Some theories suggest that primordial gravitational waves generated during inflation left a distinct swirl pattern in this polarization, a smoking gun for the Big Bang's explosive birth. Perhaps the most tantalizing possibility is that the CMB might hold clues to what came before the Big Bang. Certain anomalies in the data, unexpectedly large cold spots or curious alignments of fluctuations, have led some physicists to speculate about collisions with other universes in a multiverse, or cyclical models where our universe is just the latest in an endless series. Others propose that these quirks could be echoes of a previous cosmic phase, a universe that existed before ours, its remnants baked into the background radiation like shadows on a cave wall. What's clear is that the CMB isn't just a relic, it's an active, dynamic record. Every new generation of telescopes peels back another layer, revealing subtler patterns, finer details. Future missions might even detect traces of primordial neutrinos or dark matter imprinted in this ancient light. The cosmic microwave background is more than a window to the past. It's a mirror reflecting the universe's deepest mysteries, proving that sometimes the faintest whispers carry the loudest truths. Time crystals sound like something straight out of science fiction, but they're very real, and they defy one of the universe's most fundamental rules. Unlike ordinary crystals, which have repeating patterns in space like the lattice of a diamond, time crystals repeat in time. Picture a clock that ticks forever without any energy input, or a dance that loops endlessly without the dancers ever growing tired. That's the eerie beauty of these structures. They oscillate between states in a perfectly predictable rhythm, not because they're being pushed, but because it's their natural quantum behavior. This isn't perpetual motion in the classic sense. It's something far stranger, a fingerprint of quantum mechanics playing out on a grand scale. What makes time crystals so tantalizing for cosmic memory is their stability. Once set in motion, their rhythmic patterns persist indefinitely, unaffected by external disturbances. Think of them as the universe's most reliable metronomes, ticking away across eons without missing a beat. Some physicists speculate that if naturally occurring time crystals exist, perhaps forged in the extreme conditions of the early universe, they could act as pristine time capsules, preserving quantum information from the dawn of time itself. Imagine a cosmic vault where the quantum states of particles from 13.8 billion years ago are still perfectly intact, frozen in an endless loop of repetition. The implications are staggering. If we could find and decode these crystalline rhythms, we might uncover details about the universe's infancy that no other method can reveal. For instance, time crystals formed during cosmic inflation, the universe's explosive initial expansion, might encode the energy fluctuations of that era, offering clues about the forces that shaped the cosmos. Or consider black holes. If their violent births generated time crystals in their vicinity, those structures could still be pulsing today, carrying encrypted data about the black hole's formation. It's like stumbling upon a phonograph record from the Big Bang, its grooves etched not in vinyl but in the fabric of space-time itself. Yet the most mind-bending possibility is that time crystals might blur the line between past and present. In quantum mechanics, particles don't have definite states until they're observed, a concept called superposition. Time crystals could lock particles into superpositions that repeat cyclically, effectively creating a snapshot of quantum uncertainty that persists across time. This means a time crystal formed in the early universe might still contain particles oscillating between states that existed before galaxies even formed. It's as if the crystal is a quantum pendulum, swinging between moments in history, preserving each swing perfectly. Of course, detecting these cosmic time capsules won't be easy. Laboratory-created time crystals are fragile, requiring ultra-cold temperatures and precise conditions to maintain their rhythms. Natural ones, if they exist, would likely be hidden in the most extreme environments near neutron stars, in the remnants of primordial black holes, or floating in the vast voids between galaxies. But the hunt is already on. Advanced sensors and quantum simulators are being designed to spot the faint signatures of these temporal oddities, while theoretical models predict where they might lurk in the wild. Time crystals challenge our understanding of memory itself. We're used to thinking of the past as something fixed, immutable, a series of events locked in history. But if the universe has woven its history into these pulsing quantum structures, then the past isn't just a static record. It's a dynamic, living thing, echoing across time in perfect, unbreakable rhythms. And if we learn to listen, we might hear the universe's oldest stories, told in a language of perpetual motion. Dark matter doesn't glow, absorb light, or collide with the atoms that make up stars and planets. It's the universe's ultimate ghost, an invisible presence that reveals itself only through gravity's subtle pull. But this very invisibility might make it the cosmos's most reliable historian. While ordinary matter blazes, burns, and transforms, dark matter simply watches, its distribution sculpted over billions of years by the gravitational tug of war between galaxies. Imagine a cosmic battlefield where the warriors' stars and gas flare brightly and fade, while the silent spectators, dark matter, remain unchanged, their positions mapping every skirmish, every collision, every merger in perfect, undisturbed detail. The evidence for this lies in the way dark matter bends light. When astronomers peer at distant galaxies, they often see them distorted, stretched into smears or rings. This phenomenon, called gravitational lensing, happens because the gravity of dark matter warps space-time, bending the path of light like a funhouse mirror. But these distortions aren't random, they're cosmic breadcrumbs, tracing the distribution of dark matter across the universe. By analyzing these patterns, scientists can reconstruct the hidden scaffolding of dark matter that holds galaxies together, revealing scars from ancient collisions long after the visible fireworks have faded. Take the Bullet Cluster, for example. This pair of galaxy clusters collided hundreds of millions of years ago, and the aftermath is a forensic gold mine. The hot gas from the clusters, visible in X-rays, slowed and pooled in the collision's wake, but the dark matter, detected through gravitational lensing, sailed straight through, barely interacting. The result, a perfect separation of ordinary and dark matter, like a cosmic chalk outline marking where the clusters once were. This isn't just a curiosity, it's proof that dark matter preserves a record of cosmic violence in ways visible matter can't. But the story gets even richer when we zoom out. The universe's large-scale structure, a vast web of filaments and voids, is shaped primarily by dark matter's gravitational pull. Ordinary matter simply follows its lead, pooling where dark matter's gravity is strongest. This means the cosmic web isn't just a snapshot of today's universe. It's a fossilized imprint of the universe's growth over billions of years. By simulating how dark matter clumps and spreads, cosmologists can rewind the tape, reconstructing how galaxy clusters formed, how filaments stretched, and how voids expanded. It's like reading tree rings, but on a scale so vast it encompasses the entire observable cosmos. The most tantalizing possibility is that dark matter might encode information about the universe's earliest moments. Some theories suggest dark matter particles could be relics from the Big Bang, their present-day distribution reflecting quantum fluctuations from the universe's first seconds. If so, mapping dark matter with ever greater precision using next-generation telescopes like the Vera Rubin Observatory or the Euclid Space Mission could let us peer back to a time before stars, before atoms, even before light could travel freely. Dark matter might be the only witness to eras otherwise lost to time, a silent scribe recording the universe's first whispers, and then there's the mystery of dark matter's clumpiness. Simulations predict that dark matter should form dense, granular halos around galaxies, but observations suggest it's smoother than expected. This discrepancy could hint at unknown interactions between dark matter particles, or even entirely new physics. If dark matter isn't as passive as we thought, its subtle behaviors might encode a richer history like ink fading on an ancient scroll. One thing is certain. Dark matter isn't just a placeholder for gravity's missing mass. It's a living archive, its structure telling a story of cosmic evolution written in the language of gravity. As we refine our ability to map its invisible contours, we're not just solving a modern astronomical puzzle, we're learning to read the universe's autobiography, penned in the quiet, enduring script of the unseen. We experience time as an arrow, flying irrevocably from past to future, but why does it feel this way? The answer may lie in entropy, one of the universe's most fundamental yet misunderstood forces. At its core, entropy measures disorder, the slow unraveling of structured systems into chaos. A shattered glass doesn't spontaneously reassemble, smoke disperses but never reforms into a neat column. These everyday examples reveal a profound cosmic truth. Entropy always increases, carving an irreversible direction into the fabric of reality itself. This relentless march toward disorder is what gives us the psychological sensation of time's flow, the feeling that yesterday is fixed while tomorrow remains unwritten. But entropy isn't just a destroyer of order. Some physicists propose it could also be the universe's most meticulous archivist. Imagine a cosmic crime scene where entropy gradients variations in disorder across space act like timestamps. A supernova's aftermath, for instance, leaves behind expanding debris where entropy spikes at the explosion's epicenter and tapers off at the edges. These gradients aren't random, they're thermodynamic fingerprints, marking when and where the event occurred. If we could map these subtle differences in disorder across the cosmos, we might reconstruct a timeline of ancient cataclysms, like reading layers of sediment in a geological dig. The implications stretch even further. Black holes, those infamous entropy factories, might hold the ultimate records. According to the laws of thermodynamics, a black hole's surface area, its event horizon directly correlates with its entropy. As matter falls in, the horizon grows and entropy skyrockets. But here's the twist: Hawking radiation, the slow leakage of energy from black holes, carries away entropy in precise, measurable amounts. This means a black hole's evaporation isn't just a fade to black. It's a controlled release of encoded history, like a cosmic ticker tape recording its life story. What's truly wild is how this challenges our perception of time's arrow. We think of the past as immutable and the future as uncertain, but entropy gradients suggest the past might still be hiding in plain sight. Consider the cosmic microwave background. Its near-uniform glow isn't perfectly smooth. Tiny temperature variations reflect entropy differences frozen in time when the universe was a mere infant. These imperfections aren't just relics, they're active clues, whispering secrets about how entropy sculpted the cosmos from its earliest moments. Could we one day decode these thermodynamic breadcrumbs? Emerging theories in quantum gravity hint that spacetime itself might preserve entropy patterns like grooves in a vinyl record. Advanced simulations already model how entropy fluctuations in the early universe seeded galaxy formation. But future telescopes could take this further, searching for entropy imprints left by events predating stars themselves. The key lies in recognizing that entropy isn't just chaos, it's chronology. Every time you stir cream into coffee, you're not just mixing liquids, you're participating in the universe's grand, irreversible act of memory-making, where even disorder tells a story. Wormholes have long captured our imagination as cosmic shortcuts, tunnels through spacetime that could connect distant galaxies or even different eras. But beyond their science fiction allure, these hypothetical structures might serve a far more profound purpose: preserving the universe's history. Picture a wormhole not as a mere passageway, but as a celestial hard drive, its very geometry encoding data about the spacetime it traverses. Just as tree rings record centuries of growth, a wormhole structure could chronicle the gravitational tides and cosmic events it's endured. etching every twist and turn into its fabric. The idea hinges on how wormholes might form. Theoretical models suggest they could emerge from the extreme warping of space-time, perhaps near black holes or during the universe's infancy. If one end of a wormhole were anchored in the distant past while the other extended into the present, the tunnel itself could act as a frozen snapshot of that earlier era. Light, gravitational waves, or even quantum information falling into the past mouth might reverberate through the wormhole's throat, leaving echoes detectable at the other end. It's like shouting into a canyon and hearing your voice return, but instead of sound, the canyon walls are space-time itself, and the echoes carry whispers from billions of years ago. What makes this concept so compelling is how it aligns with Einstein's equations. General relativity allows for wormholes, though they'd require exotic matter, a substance with negative energy, to stay open. While we've yet to find such matter, its hypothetical existence hints at a universe where space-time isn't just a stage but an active participant in memory. A stable wormhole could theoretically preserve quantum states or gravitational imprints unchanged, like a cosmic fly trapped in amber. Imagine detecting a wormhole today and discovering it contains pristine light from a star that died before Earth formed, or quantum fluctuations from the Big Bang's aftermath, perfectly preserved in transit. But wormholes might not just store data passively, they could actively process it. Some theories propose that the interplay of quantum entanglement and wormhole geometry could create a form of natural computation, where information is scrambled and reassembled as it traverses the tunnel. This mirrors the holographic principle's claim that black holes encode information on their surfaces. Wormholes might do the same, but with the added dimension of time. If true, a wormhole could be less like a tunnel and more like a cosmic loom, weaving threads of past and present into a coherent tapestry. The challenge, of course, is finding one. Wormholes, if they exist, would likely be microscopic, hidden in the quantum foam of space-time or lurking near singularities. Yet even their shadows could leave traces, anomalies in gravitational lensing patterns, unexpected particle pairings, or distortions in the cosmic microwave background. Future telescopes tuned to detect subtle space-time ripples might spot these fingerprints, while quantum sensors could hunt for microscopic wormholes flickering in and out of existence. Whether wormholes are time machines, data vaults, or both, their potential to rewrite cosmic history is undeniable. They remind us that space-time isn't just empty expanse but a dynamic, information-rich medium where the past might not be lost, just waiting, curled up in some hidden dimension for us to learn how to listen. Beneath the smooth, predictable surface of space-time lies a hidden chaos, a seething, bubbling froth where the rules of classical physics break down. This is quantum foam, the universe's most fundamental layer, where space and time cease to be stable and instead churn like a boiling ocean at scales a billion times smaller than an atom. Here, virtual particles pop in and out of existence in a frenzied dance, borrowing energy from the vacuum itself before vanishing back into oblivion. These fleeting fluctuations aren't just random noise. They might be the universe's earliest scribbles, tiny imprints left over from a time before stars, before matter, even before light could travel freely. What makes quantum foam so extraordinary is how it could preserve traces of the cosmos's infancy. Imagine the universe moments after the Big Bang, a realm of unimaginable energy where space-time itself was turbulent and malleable. As the cosmos expanded and cooled, that primordial turbulence didn't just vanish, it froze into the fabric of reality, like waves solidifying into glass. Today, the remnants of that chaos might still writhe at the smallest scales, a fossil record written in the language of quantum mechanics. If we could peer into this foam, we might glimpse the universe's first thoughts, the quantum fluctuations that later grew into galaxies and galactic superclusters. The challenge lies in detecting something so infinitesimally small. Quantum foam operates at the Planck scale, far beyond the resolution of any microscope. But indirect clues are everywhere. Black holes, for instance, might reveal its presence. When matter falls into a black hole, it's crushed to unimaginable densities, potentially probing the foam's structure. Some theories suggest that the Hawking radiation leaking from black holes carries subtle fingerprints of this quantum turbulence, like steam rising from a boiling pot. Even empty space isn't truly empty. It crackles with zero-point energy, a faint hum of quantum activity that could be the echo of that ancient froth. Another tantalizing possibility is that quantum foam could hold clues about the universe's pre-Big Bang state. Certain models of quantum gravity propose that our cosmos emerged from a previous phase, a collapsing universe or a collision of higher dimensional branes. The foam's structure might encode scars from that earlier epoch, like scars on tree bark telling the story of past storms. If so, studying its properties could let us peer beyond time's conventional horizon, answering questions like, was there a before the Big Bang? Did spacetime always exist, or did it crystallize from something even stranger? The implications stretch beyond cosmology. Quantum foam could redefine our understanding of information itself. In a universe where spacetime is fundamentally grainy, every event, every collision, every birth of a star might leave behind minute distortions in the foam's texture. These wouldn't be memories in the human sense, but topological imprints like knots tied in an endless rope. Future technologies, perhaps harnessing quantum entanglement or ultra-precise gravitational wave detectors, might one day decode these knots, reconstructing cosmic history from the bottom up. Yet the most profound idea is this: if quantum foam truly retains fluctuations from the universe's first moments, then the past isn't lost, it's just buried deeper than we've ever dug. The foam isn't a passive backdrop. It's an active participant in the cosmos's story, a subatomic scratchpad where the universe jotted down its earliest notes. And if we learn to read them, we might finally understand how everything from the tiniest particle to the grandest galaxy emerged from that primordial chaos. Neutrinos are the universe's ultimate ghosts. Billions pass through your body every second, leaving no trace. These nearly massless particles barely interact with matter, slipping through planets and stars as if they weren't even there. But this same aloofness makes them extraordinary cosmic messengers. While light gets delayed, scattered, or absorbed by dust and gas, neutrinos race across the cosmos unimpeded, carrying untouched information from the most violent events in the universe. When a star explodes in a supernova, for instance, its light takes time to fight through the debris, but neutrinos burst outward at nearly the speed of light, arriving hours before the visible fireworks. In 1987, detectors on Earth caught a handful of neutrinos from a supernova in the Large Magellanic Cloud, marking the first time these elusive particles gave us a real-time alert of a stellar death happening 168,000 light-years away. But neutrinos don't just herald stellar explosions, they could be time capsules from the universe's birth. In its first seconds, the cosmos was so dense and hot that even neutrinos, which rarely interact, were trapped in the primordial soup. As the universe expanded and cooled, they broke free, streaming outward in all directions. This cosmic neutrino background, a relic as fundamental as the cosmic microwave background, still permeates space today. If we could detect these ancient neutrinos, they'd offer a snapshot of the universe just 1 second after the Big Bang, a time when quarks were still forming protons and neutrons. Unlike the microwave background, which shows us the universe at 380,000 years old, neutrino background would take us back almost to the very beginning, revealing conditions far hotter and more extreme than anything we've ever observed. The challenge is catching them. Neutrinos are so evasive that detectors must be enormous, like Japan's Super Kamiok, and a tank filled with 50,000 tons of ultra-pure water, buried deep underground to shield it from other particles. Even then, only a tiny fraction of neutrinos leave a detectable trace, but next-generation experiments like the Deep Underground Neutrino Experiment DUNE aim to change that. Using liquid argon and cutting-edge sensors, DUNE could pinpoint not just the direction of incoming neutrinos but their energy and type, letting us reconstruct cosmic events with unprecedented clarity. Imagine tracking a neutrino back to a supernova that hasn't even brightened in our telescopes yet, or decoding fluctuations in the cosmic neutrino background to map the universe's infancy. What's truly staggering is how much we still don't know. Neutrinos oscillate between three flavors: electron, muon, and tau as they travel, a discovery that earned the 2015 Nobel Prize. But why do they have mass at all? The standard model of particle physics predicted they'd be massless, so their tiny weight hints at new physics beyond our current understanding. Some theories suggest neutrinos might be their own antiparticles, a property that could explain why the universe is made of matter instead of antimatter. Others propose that sterile neutrinos, an even more elusive variety, could be hiding in plain sight, influencing galaxy formation or even dark matter. Every neutrino that streaks through Earth is a whisper from the distant cosmos, untouched by magnetic fields, unaltered by interstellar dust. They're the closest thing we have to a pristine signal from the universe's most explosive and enigmatic events. And as detectors grow more sensitive, we're not just building better tools, we're learning to listen to a language older than stars, written in the faintest ink imaginable. The next time you feel a breeze, remember, trillions of neutrinos are passing through you right now, each one a silent witness to the universe's untold stories. The question is, how many more secrets will they reveal when we finally learn to hear them? Cosmic strings are like the universe's stretch marks, scars left over from a time when reality itself was undergoing growing pains. Picture the early cosmos, a seething cauldron of energy and force fields cooling rapidly after the Big Bang. Just as cracks form in ice as it freezes, space-time might have developed one-dimensional defects, infinitely thin but unimaginably dense filaments stretching across the universe like cosmic spider silk. These aren't just theoretical curiosities, they're potential time capsules vibrating with secrets from the universe's first trillionth of a second. What makes cosmic strings so fascinating is how they could act as natural gravitational wave generators. Unlike black holes or neutron stars, which produce gravitational waves through violent collisions, cosmic strings would hum with energy simply by existing. Their immense tension, some models suggest a single string just a mile long could weigh as much as an entire planet, would cause them to oscillate at relativistic speeds, sending ripples through space-time itself. These wouldn't be the sharp chirps detected by LIGO, but a steady, almost musical drone, a background hum woven into the fabric of the cosmos. If we could tune into this frequency, it might reveal details about cosmic inflation, that brief period when the universe expanded faster than light, stretching quantum fluctuations into the seeds of galaxies. The real magic lies in how these strings could encode information. Their vibrations wouldn't be random, they'd reflect the exact conditions of their formation during the universe's phase transitions, moments when fundamental forces like electromagnetism and the strong nuclear force split apart. Think of it like a vinyl record. The grooves are etched by the universe's birth pangs, and the needle is space-time itself, playing back a song from the dawn of time. Some theories even suggest that cosmic strings could form loops, collapsing and reconnecting in ways that leave behind distinctive gravitational wave signatures, like a drummer keeping rhythm for the cosmos. Detecting these filaments won't be easy. They'd be thinner than a proton, yet so dense their gravity could bend light around them, creating telltale double images of distant galaxies, a phenomenon called gravitational lensing. Astronomers have searched for these lensing patterns, but so far no definitive cosmic string has been found. That doesn't mean they're not out there. They might simply be rarer or fainter than predicted. Future observatories like the Laser Interferometer Space Antenna LISA could change the game by picking up their low-frequency gravitational waves, sounds too deep for current detectors to hear. What's wild is that cosmic strings might not just be relics, they could still be forming. In certain theories, high-energy processes in today's universe, like the interiors of neutron stars or even particle colliders, might spawn tiny, short-lived strings. These wouldn't span galaxies, but they'd offer a lab-scale glimpse into the physics of the early cosmos. It's like finding a living dinosaur, but instead of bones, it's a wrinkle in space-time humming a tune from the beginning of everything. Whether cosmic strings exist or not, their possibility forces us to rethink space-time as something more dynamic, more textured than an empty stage. They remind us that the universe's history isn't just written in light or matter, but in the very geometry of reality, a story told in vibrations waiting for us to press play. The multiverse hypothesis turns the universe from a singular story into an endless library, where every possible outcome of every quantum decision plays out across infinite branching realities. Picture a book with countless pages, each page a self-contained universe with its own laws of physics, its own history, even its own version of time. Some might be nearly identical to ours, differing only in the spin of a single electron billions of years ago. Others could be unrecognizable, with gravity repelling instead of attracting, or light moving in jagged lines instead of straight rays. But here's the twist: the boundaries between these universes might not be impermeable walls. They could be active membranes, vibrating with data about the alternate histories playing out just beyond our reach. One tantalizing possibility is that these boundaries act like cosmic hard drives, encoding information about neighboring universes in their structure. Think of it like two soap bubbles pressed together. The surface where they meet isn't just empty space. It's a dynamic interface shimmering with energy and potential. In the same way, the edges of our universe might ripple with gravitational echoes from other realities, faint imprints left by cosmic events that never happened here. These wouldn't be full-blown messages, more like shadows cast on a wall, hinting at shapes we can't quite see. Gravity could be the key to detecting these whispers. If a black hole in a parallel universe collided with one in ours, the resulting space-time tremors might carry a distinctive signature, like a chord played in a distant room. Advanced gravitational wave detectors, like the proposed Einstein telescope, might one day pick up these anomalous ripples, revealing collisions that shouldn't exist, or better yet, ripples with no apparent source in our observable cosmos. Even more intriguing are anomalies in the cosmic microwave background. Some theorists suggest that cold spots or unusual polarization patterns could be bruises from long ago encounters with other universes, like fingerprints left on glass. But the multiverse's memory might not just be stored at the boundaries. Quantum entanglement could create threads linking universes, preserving correlations between them long after they've diverged. Imagine two particles born in the same quantum state, then separated as their universes branched apart. Even across realities, they might remain mysteriously connected, their entangled states acting as a living record of their shared origin. Decoding these quantum links could be like finding a letter slipped between the pages of a book, a note from another version of reality saying, "We were here too." The wildest implication: if the multiverse is real, then every choice you've ever made, and every choice you didn't, exists somewhere in this cosmic library. The version of you who took that job overseas, the one who never left their hometown, even the one who became an astronaut or a baker or never existed at all. Their stories are all written into the fabric of the multiverse, preserved in spacetime's infinite archive. We might never visit those alternate pasts, but their gravitational echoes could still brush against our reality, reminding us that history isn't a single thread. It's a tapestry woven from every possibility that ever was or ever could be. Black holes have always been the ultimate cosmic enigmas, regions where gravity is so intense that not even light can escape. But there's a deeper mystery lurking at their edges, one that shakes the very foundations of physics: the information paradox. At its core, this paradox asks a haunting question: when something falls into a black hole, is all the information about it truly erased from existence? If so, it violates one of quantum mechanics' most sacred principles. Information can never be destroyed, only transformed. Imagine tossing a book into a fire. The pages burn, but in theory, if you could track every ash particle and photon of heat, you could reconstruct the book. But a black hole seems to defy this logic. It doesn't just burn the book, it swallows it whole, leaving no trace behind. Stephen Hawking's groundbreaking work in the 1970s suggested that black holes slowly evaporate over eons, emitting what we now call Hawking radiation. But here's the catch: this radiation appeared to be thermal, random noise carrying no information about what fell in. It was as if the universe had a shredder, and black holes were its ultimate document destroyers. This idea sent shockwaves through physics, because if information could vanish without a trace, it would mean our understanding of reality was fundamentally flawed. The implications ripple far beyond black holes. It would imply that the universe itself has no reliable memory, that the past could be erased as easily as chalk from a blackboard. But nature rarely lets paradoxes stand unresolved. In recent years, physicists have proposed radical solutions that turn black holes from cosmic shredders into sophisticated archivists. One idea is the firewall hypothesis, a blazing wall of energy just inside the event horizon that scrambles information into Hawking radiation before it's lost forever. Picture a black hole not as a pit, but as a cosmic blender, churning everything it consumes into a fine, information-rich mist that slowly leaks back into the universe. Another theory, dubbed soft hair, suggests that black holes aren't bald after all. They're covered in faint, quantum hairs that imprint information about infalling matter onto their event horizons. These hairs wouldn't be physical strands, but subtle distortions in spacetime itself, like grooves on a record preserving the universe's soundtrack. The stakes couldn't be higher. If black holes preserve information, even in ways we don't yet understand, it would mean the cosmos has a failsafe, a way to ensure no event, no matter how catastrophic, is ever truly forgotten. This wouldn't just solve a theoretical puzzle. It would redefine our understanding of cosmic memory. Every supernova, every collision, every particle that ever crossed a black hole's threshold might still be encoded in the fabric of reality, waiting to be decoded. Future experiments like detecting the quantum properties of Hawking radiation or simulating black holes in quantum computers could finally crack this code. What's truly fascinating is how this paradox forces us to rethink the nature of reality itself. If information can't be destroyed, then time isn't just a sequence of events, it's a narrative, a story written into the universe's structure. Black holes, once thought to be the end of the story, might instead be its most cryptic chapters, written in a language we're only beginning to decipher. And if we can learn to read them, we might discover that nothing, not even the darkest depths of space, can erase the past completely. Massive objects don't just bend space, they bend light itself, turning the cosmos into a hall of mirrors where reality distorts in the most extraordinary ways. This phenomenon, called gravitational lensing, is one of nature's most elegant tricks. Picture a galaxy so massive that its gravity warps space-time around it, curving the path of light from objects behind it like a funhouse mirror. The result: distant galaxies aren't just magnified, they're stretched, duplicated, even twisted into surreal rings called Einstein rings, named after the physicist who predicted this effect over a century ago. But these cosmic mirages aren't just pretty to look at, they're forensic tools, revealing secrets about the invisible scaffolding of the universe. What makes gravitational lensing so powerful is how it exposes the hidden hand of dark matter. When astronomers map the distorted images of background galaxies, they're not just seeing the gravity of visible stars and gas, they're tracing the influence of dark matter's immense, invisible halos. Take the Bullet Cluster, where two galaxy clusters collided like cosmic freight trains. The visible gas slowed and pooled in the wreckage, but the lensing patterns revealed something astonishing. The dark matter sailed straight through, its gravity bending light in ways that betrayed its presence. This was smoking gun evidence that dark matter isn't just theoretical, it's real, it's out there, and it's sculpting the universe in ways we're only beginning to understand. But lensing does more than reveal dark matter. It lets us rewind cosmic history. The light from a lensed galaxy might have traveled for billions of years before reaching us, meaning we're seeing it as it was when the universe was young. By analyzing how that light gets twisted, astronomers can reconstruct the distribution of matter along its path, like tracing the path of a bullet through fog. This turns lensing into a time machine, allowing us to map how galaxies and clusters grew over eons. For instance, subtle distortions called weak lensing show how cosmic filaments, the universe's vast, web-like structures, have stretched and evolved, offering clues about the tug of war between dark matter's gravity and dark energy's repulsive push. The most mind-bending application, using lensing to study the universe's expansion. When light from a distant supernova gets lensed, it can arrive at Earth via multiple paths, creating duplicate images. But because each path is a different length, the light doesn't arrive simultaneously. There's a delay, sometimes years apart. By measuring these delays, scientists can calculate the Hubble constant, the rate at which the universe is expanding. It's like cosmic clockwork, with space-time itself serving as the gears. Future telescopes like the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope will take lensing to new heights, mapping billions of galaxies and their distortions with unprecedented precision. These projects won't just sharpen our view of dark matter, they'll test whether gravity itself behaves differently across cosmic distances, probing the edge of Einstein's theory. Every warped galaxy, every Einstein ring, every faint distortion is a clue, a fingerprint left by the universe's hidden architecture. And as we learn to read them, we're not just seeing the cosmos as it is, we're decoding the story of how it came to be. A quantum vacuum is anything but empty. It crackles with an invisible energy, a seething sea of particles flickering in and out of existence so quickly they defy observation. This isn't just background noise, it's the universe's foundational layer, a simmering reservoir of potential where the rules of reality are written. But what if this vacuum isn't as stable as it seems? Some theories suggest it could be teetering on a knife's edge, a metastable state that might one day collapse into a lower energy configuration, like a ball perched on a hill finally rolling into the valley below. If that happened, the consequences would be unimaginable, a wave of transformation sweeping through the cosmos at the speed of light, rewriting the laws of physics in its wake. Stars, planets, even atoms themselves could dissolve into new forms, erasing the universe as we know it in an instant. Yet before such a catastrophic reset, this unstable vacuum might serve an unexpected purpose, preserving the universe's history like a cosmic backup drive. Every fluctuation, every ripple in the quantum foam could encode data about the state of reality before the decay. Think of it like a frozen lake moments before it cracks. The patterns in the ice hold a record of every footstep, every gust of wind that came before. In the same way, the vacuum's subtle tremors might contain imprints of earlier cosmic epochs, snapshots of physics as it once was. Some physicists speculate that if we could measure these fluctuations with enough precision, we might uncover traces of the universe's previous configurations, perhaps even evidence of multiple vacuum states stacked like layers in an archaeological dig. The key lies in understanding false vacuums. Our universe might exist in a temporary energy well, stable for now but not eternally secure. If a quantum tunnel event occurs, a rare but possible leap to a lower energy state, it could trigger vacuum decay. But here's the twist: the very act of tunneling leaves fingerprints. Quantum field theory suggests that the transition wouldn't be instantaneous. There'd be a phase where the old and new vacuums coexist, their boundaries vibrating with information about both states. These boundary layers, or domain walls, could act like cosmic film negatives, preserving data about the universe's prior conditions. Imagine finding a sealed letter from a civilization long gone, except the letter is space-time itself, and the ink is written in the language of quantum fields. Detecting these signals wouldn't be easy. The energy scales involved are mind-bogglingly small, far beyond our current instruments, but there are tantalizing hints. Some models predict that vacuum fluctuations could influence the behavior of fundamental particles in detectable ways, creating subtle anomalies in experiments like the Large Hadron Collider. Others propose that certain patterns in the cosmic microwave background, those faint whispers of the Big Bang, might reveal regions where the vacuum's energy once differed, like scars from ancient near collapses. The most profound implication: if the vacuum stores information about prior states, then even a cosmic reset might not be the end. Like a computer rebooting but retaining hidden system files, the universe could carry forward fragments of its past into new iterations. This opens the door to wild possibilities. Could vacuum decay be less of an erasure and more of a transformation, a way for the cosmos to evolve while preserving echoes of what came before? The answer might lie in the quantum foam beneath our feet, humming with secrets older than time itself. Cyclic cosmology paints a picture of the universe not as a one-time event, but as a cosmic phoenix rising from its own ashes in an endless loop of destruction and rebirth. Imagine a cosmos that expands until gravity finally wins, pulling everything back into a fiery crunch, only to rebound in another Big Bang, over and over across eternity. This isn't just poetic symmetry. It's a serious scientific hypothesis with roots stretching back to the 1930s, when physicists first toyed with the idea of an oscillating universe. But here's the twist: if these cycles are real, they might not be perfect resets. Like footprints in wet concrete, each iteration could leave faint traces in the next, turning the universe into a palimpsest, a parchment where old writings show through beneath the new. The key to unlocking these cosmic layers lies in the universe's most extreme moments, during the Big Crunch, when all matter and energy collapse into a singularity. Quantum effects could imprint subtle irregularities onto the next cycle's Big Bang. Think of it like a cosmic game of telephone, where each iteration slightly distorts the message but never erases it completely. these distortions might manifest in the cosmic microwave background, those faint afterglow patterns from the early universe. Anomalies like the infamous cold spot, a mysteriously large patch of cooler radiation, could be bruises from a pre-Big Bang collision, or echoes of structures from a previous cycle that somehow survived the reboot. Even black holes might serve as time capsules between cycles. In some models, these gravitational monsters don't entirely evaporate during the crunch. Instead, their event horizons could act like cosmic freezers, preserving quantum information through the transition. When the next universe emerges, these relics, dubbed black hole fossils, might reappear, their Hawking radiation carrying encoded data about the previous cycle. It's as if the universe left itself sticky notes, reminders of what came before, but the most tantalizing evidence could come from dark energy. In our current cycle, this mysterious force is accelerating the universe's expansion. But in cyclic models, dark energy's behavior might change over eons, waxing and waning with each iteration. If we detect patterns in how galaxies are flying apart, subtle accelerations or decelerations that don't fit standard models, it could hint that we're seeing the tail end of a much longer rhythm, like the final beats of a song that's been playing for eternity. The implications are staggering. If cyclic cosmology is correct, then our universe isn't just 13.8 billion years old. It's one chapter in an epic with no beginning or end. The atoms in your body might have been forged not just in this universe's stars, but in stars from countless cycles before, their quantum histories stacked like pages in an infinite book. And if we learn to read those pages, we might discover that time isn't a line, it's a spiral, winding forever through the dark. Neutron stars are cosmic extremes, stellar corpses so dense that a single teaspoon of their material would weigh billions of tons here on Earth. These incredible objects form when massive stars, many times heftier than our Sun, exhaust their nuclear fuel and collapse under their own gravity. The resulting explosion, a supernova, scatters most of the star's outer layers into space, while the core crushes down into a sphere no larger than a city, yet packing more mass than our entire Sun. The physics at play here is mind-bending. Protons and electrons are squeezed together so violently that they merge into neutrons, creating a material so compact it defies ordinary matter. But beyond their sheer density, neutron stars might hold something even more valuable, a record of the universe's most violent moments, etched into their very surfaces like cosmic braille. Take their crusts, for instance. The outer layers of neutron stars are thought to be crystalline, a lattice of atomic nuclei, so tightly packed they form a solid shell harder than diamond. When these stars are born in supernova, the unimaginable forces at play could imprint permanent deformations onto this crust, like dents in a cosmic armor. Some researchers speculate that passing gravitational waves, ripples from distant black hole collisions, or even the neutron star's own birth throes might leave detectable wrinkles on this ultra-dense surface. It's as if these stars are recording every seismic event they experience, preserving them in a language of atomic distortions we're only beginning to decode. Then there's the wild behavior of their magnetic fields. Neutron stars often possess magnetic fields trillions of times stronger than Earth's, turning them into cosmic lighthouses that beam radiation across the galaxy as they spin. These beams, detected as regular pulses of light, give them the name pulsars. But here's where it gets fascinating. Irregularities in these pulses, tiny hiccups in their otherwise perfect rhythms, could be the result of ancient trauma. A close encounter with another star, a particularly violent gravitational wave, or even a collision with an asteroid-like object might have jostled the star's rotation, leaving a permanent fingerprint in its pulse pattern. By studying these anomalies, astronomers might reconstruct events that happened billions of years ago, like detectives piecing together a crime scene from a single smudged fingerprint. Perhaps the most tantalizing possibility lies in neutron star mergers. When two of these ultra-dense objects spiral into each other, they create gravitational waves detectable across the universe, but they also forge heavy elements like gold, platinum, and uranium in their aftermath. The debris from these collisions spreads through space, seeding future generations of stars and planets. But the neutron stars themselves might retain scars from the encountered, distortions in their internal structure or crust that encode details about the merger. If we could study one up close, we might find a Rosetta Stone for understanding how the universe's heaviest elements are made and how often these cataclysmic events occur. The challenge, of course, is distance. Neutron stars are small, dark, and often thousands of light years away, but new technologies are bringing them within reach. Radio telescopes like the upcoming Square Kilometre Array will listen for subtle changes in pulsar signals, while gravitational wave detectors hunt for the ripples from their collisions. Some scientists even propose sending robotic probes to nearby neutron stars, though the engineering hurdles like surviving their crushing gravity and deadly radiation are staggering. What's clear is that neutron stars aren't just cosmic oddities, they're time capsules, locking away secrets from the universe's most turbulent eras. Every quake in their crust, every glitch in their spin, every ripple in their magnetic field could be a message from the past, waiting for us to learn how to listen. And when we do, we might uncover stories written not in ink or stone, but in the twisted nuclei of matter itself. Quantum gravity isn't just about reconciling two conflicting theories. It's about rewriting our understanding of how the universe remembers itself. At the tiniest scales, where space-time frays into a seething quantum foam, the smooth geometry of Einstein's relativity shatters into uncertainty. Here, the very fabric of reality might consist of discrete, indivisible units like pixels on a cosmic screen, each carrying fragments of information about the past. Loop quantum gravity, one of the leading approaches, imagines space-time as a network of interwoven threads, where every knot and connection encodes a quantum of area or volume. These loops don't just define space, they could also store data, like microscopic etchings on the universe's foundational layer. Picture an ancient tapestry, its threads frayed but still holding the patterns of long-lost stories. If this model holds, then every event, from the birth of a star to the collapse of a black hole, might leave traces in this woven structure, a cosmic ledger written in the language of knots and twists. String theory offers a radically different but equally mesmerizing vision. Instead of point-like particles, it posits that the universe's building blocks are vibrating strings, each oscillation corresponding to a different particle or force. But here's the twist. These strings don't just dance in space-time, they create it. The theory suggests that space-time emerges from the collective behavior of strings, like the surface of a lake arising from countless molecular interactions. In this view, cosmic memory could be embedded in the way strings vibrate and interact across higher dimensional membranes, or brains. Imagine plucking a guitar string and hearing not just a note, but an echo of every time it was plucked before. If space-time is truly built from strings, then its history might be preserved in their harmonics, a symphony of vibrations stretching back to the Big Bang. Yet another perspective comes from causal set theory, which proposes that space-time is fundamentally discrete, a collection of discrete events linked by cause and effect, like beads on an endless necklace. In this framework, the past isn't a smooth continuum but a precise sequence of moments, each connected to the next in an unbreakable chain. The beauty of this idea lies in its simplicity. information isn't stored in geometry or vibrations but in the relationships between events. A supernova's explosion, a planet's formation, even your last breath, each would be a bead in the cosmic necklace, its position forever fixed in the causal web. This could explain why the past feels immutable while the future remains open. The universe's memory is literally built into its structure, one cause leading irrevocably to the next. The stakes couldn't be higher. If quantum gravity reveals how spacetime retains information, it could resolve black hole paradoxes, illuminate the nature of time, and even hint at what preceded the Big Bang. Current experiments like tabletop quantum simulators or precision measurements of gravitational waves are probing these theories indirectly, searching for telltale signs of spacetime's granularity or extra dimensions. Some models predict that if spacetime is pixelated at the Planck scale, high-energy cosmic rays might reveal subtle anomalies in their behavior, like digital artifacts in an otherwise analog universe. Others suggest that the afterglow of the Big Bang could contain imprints of pre-Big Bang physics, hidden in the polarization patterns of the cosmic microwave background. What's truly thrilling is how these theories transform our view of cosmic memory. Spacetime isn't just a passive backdrop, it's an active participant, a dynamic medium that encodes, processes, and possibly even computes information. Whether through loops, strings, or causal sets, the universe might be less like a static archive and more like a living brain, its connections humming with the weight of everything that's ever happened. And if we can decipher its language, we might finally answer the oldest question of all. How does the cosmos remember itself? Cosmic inflation is like the universe hitting the fast-forward button, only instead of seconds. It rewrote the entire fabric of reality in a fraction of a second. Picture the cosmos in its infancy, smaller than a single atom, when suddenly an unimaginable force, dubbed the inflaton field, propelled it to expand faster than the speed of light. In less time than it takes light to cross a proton, the universe grew by a factor of 10 to the power of 26, smoothing out irregularities and locking in quantum fluctuations that would shape everything to come. But here's the mind-blowing part. Those fluctuations weren't erased. They were stretched, amplified, and frozen into the very architecture of spacetime, like fingerprints pressed into wet clay and then baked solid. What's astonishing is how these microscopic quantum jitters became the blueprints for galaxies. Imagine a quiet pond suddenly hit by a rainstorm. Each raindrop creates tiny ripples. Now picture that pond expanding to the size of an ocean in an instant. Those ripples now vast waves spanning continents. Inflation did exactly that to the universe, transforming subatomic quantum noise into the seeds of superclusters and voids. When the cosmic microwave background, the afterglow of the Big Bang, was first mapped, scientists found its temperature varied by mere millionths of a degree. These minuscule hot and cold spots weren't random. They were the stretched-out quantum fluctuations from inflation, cosmic fossils from the universe's first trillionth of a second. The real magic lies in how these patterns connect to today's universe. The slight overdensities in the early cosmos regions where inflation stretched matter a hair thicker became gravitational wells, pulling in more gas and dark matter over billions of years. These grew into the galaxies and galaxy clusters we see now, their distribution tracing back directly to those primordial wrinkles. It's as if inflation took a snapshot of quantum chaos and projected it onto the sky at a scale so vast, we're still deciphering its patterns 13.8 billion years later. But inflation didn't just structure matter, it also left echoes in the vacuum of space itself. Theoretical models suggest that gravitational waves generated during inflation might have imprinted a unique swirl pattern in the polarization of the cosmic microwave background. Detecting this signal, often called the smoking gun of inflation, would be like finding the universe's first selfie, a blurry but priceless image of its explosive birth. Experiments like the upcoming Light-Bird satellite or the Simons Observatory are hunting for these swirls with instruments sensitive enough to spot a fraction of a billionth of a degree. The wildest implication: if inflation's quantum fluctuations were truly random, they might have varied in strength across different regions. Some corners of the cosmos could have ended up denser or more rarefied purely by chance, creating a patchwork universe where the laws of physics themselves might differ in distant, inflated bubbles. This multiverse scenario is speculative, but it underscores how inflation isn't just a theory about the past. It's a window into the deepest nature of reality, where the tiniest quantum events cascade into the grandest cosmic structures. Yet for all its explanatory power, inflation remains maddeningly elusive. We don't know what triggered it, why it stopped, or whether it's happened elsewhere in a larger multiverse. What we do know is that its fingerprints are everywhere in the clustering of galaxies, the whispers of gravitational waves, and the faint afterglow of creation itself. Every time astronomers map a new slice of the universe, they're not just charting stars, they're reading the opening lines of a story written in quantum ink, a prologue so brief it lasted less than a blink, yet set the stage for everything that followed. Dark energy is the universe's greatest unsolved riddle, an invisible force pushing galaxies apart at ever-increasing speeds, as if space itself has a hidden engine set to full throttle. Unlike gravity, which pulls matter together, dark energy works in reverse, stretching the cosmos apart with a strength that defies expectation. When astronomers first discovered this accelerated expansion in the late 1990s, it sent shockwaves through physics. The universe wasn't just growing, it was doing so faster and faster, as if some unseen hand kept turning up the dial. But here's the twist: this mysterious force might be more than just a cosmic foot on the gas pedal. It could be a living record encoding secrets about the universe's past in the way it changes over time. Think of dark energy like a fading echo. If it's truly a dynamic field, something akin to the Higgs field but with repulsive gravity, its strength might have varied across cosmic history. Early in the universe's life, it could have been weaker, allowing gravity to dominate and pull matter into galaxies and clusters. Later, as space expanded and thinned out, dark energy might have surged, overpowering gravity and kickstarting the accelerated expansion we see today. This shift wouldn't just be a random fluctuation, it could carry imprints of the conditions that triggered it, like tree rings preserving the weather patterns of centuries past. By measuring how dark energy's influence has evolved, astronomers might reconstruct pivotal moments in cosmic history, from the era of galaxy formation to the transition into dark energy's current reign. The clues lie in the universe's large-scale structure. Dark energy doesn't just push galaxies apart, it shapes how they're distributed. When the cosmos was younger and denser, gravity's pull created vast filaments and clusters of galaxies, a cosmic web we can still map today. But as dark energy took over, that web began stretching thinner, its growth slowing under the influence of this repulsive force. By comparing the distribution of galaxies at different distances, and thus different epochs, scientists can trace how dark energy's grip has tightened over billions of years. Projects like the Dark Energy Survey and the upcoming Euclid Space Telescope are doing exactly this, photographing millions of galaxies to create a 3D atlas of the universe's expansion history. Each snapshot is like a frame in a time-lapse video, revealing how dark energy has sculpted spacetime itself. But the real breakthrough could come from an even stranger possibility. that dark energy isn't constant at all, but a field that decays or interacts with other cosmic components. Some theories propose it might be tied to quintessence, a hypothetical energy field that weakens over time. If true, the universe's acceleration could one day slow or even reverse, leading to a cosmic Big Crunch instead of endless expansion. Others suggest dark energy might fluctuate, leaving periodic signatures in the clustering of galaxies or the brightness of distant supernova. These variations could be the smoking gun, revealing not just dark energy's nature but the conditions that birthed it. The most tantalizing idea, dark energy might be a bridge to epochs we can't otherwise observe. If its behavior today reflects processes from the universe's first seconds, perhaps linked to inflation, that explosive initial expansion, then studying it could let us peer beyond the Big Bang's veil. It's like finding a message in a bottle washed ashore, its contents hinting at storms and tides from a sea we've never sailed. For now, dark energy remains a shadow in the data, its true identity hidden behind equations and observations. But with every new telescope, every deeper galaxy survey, we're closing in on the answer. And when we find it, we won't just solve a modern astronomical puzzle, we'll unlock a diary of the cosmos, written in the invisible ink of expanding space. The Boltzmann brain paradox is one of those ideas that starts as a quirky thought experiment and quickly spirals into an existential hall of mirrors. Imagine a lone, self-aware brain complete with fabricated memories and a false sense of history, popping into existence purely by random quantum fluctuations. No body, no universe, just a solitary consciousness convinced it's lived a full life in a world that never existed. It sounds like the plot of a dystopian sci-fi novel, but this scenario emerges straight from the bizarre logic of quantum mechanics and thermodynamics. According to the laws of probability, given enough time, even the most unlikely events become inevitable. In an infinite or near eternal universe, the random assembly of particles into a functioning brain, with all its synapses firing just right to create the illusion of a past, might not just be possible. It might be statistically unavoidable. What makes this paradox so unsettling isn't just the idea of phantom minds materializing in the void. It's the implication that our own memories, our sense of a continuous past, might be equally fragile. If a Boltzmann brain can spontaneously generate with fabricated memories of a life it never lived, how can we trust that our own recollections are anchored in reality? The universe's timeline, as we perceive it, could be riddled with glitches, fleeting moments where coherence breaks down, and false histories flicker into being like cosmic static. This isn't just a puzzle for philosophers, it's a direct challenge to how we understand cosmic memory. If space-time preserves the past in its structure, could quantum randomness corrupt those records, inserting mirages into the archive? The paradox gains teeth when you consider entropy's role. The second law of thermodynamics states that disorder always increases, but it also allows for rare, temporary decreases like a gust of wind briefly reassembling scattered leaves into a neat pile. In an unimaginably vast cosmos, these statistical flukes could assemble not just leaves but entire minds, complete with imaginary backstories. The kicker: given enough time, Boltzmann brains would vastly outnumber real, evolved consciousnesses like ours. So statistically speaking, you're far more likely to be a Boltzmann brain than a person with a genuine past. Suddenly, the question isn't just academic, it's personal. Yet the paradox isn't just a mind-bending diversion. It forces physicists to confront the limits of their models. If our theories predict that illusions should outweigh reality, does that mean the theories are flawed, or that reality itself is stranger than we dare admit? Some argue that the paradox hints at undiscovered laws preventing such aberrations, like quantum decoherence shredding unstable configurations before they achieve self-awareness. Others suggest it's evidence for a cosmological cutoff, a boundary to how far back or how wide we can extrapolate our current physics. After all, if the universe isn't infinite or eternal, the probability of Boltzmann brains plummets. The real lesson here isn't that we're all likely figments of quantum noise. It's that cosmic memory, the universe's ability to preserve and transmit information, might be more fragile or more malleable than we've assumed. Just as a glitchy hard drive can rewrite files at random, the fabric of reality might occasionally misremember, creating pockets of coherence where none should exist. This doesn't mean the past is entirely unreliable, but it does remind us that even the most fundamental aspects of existence, time, memory, identity, are subject to the universe's deepest, most unpredictable rules. And that's a humbling thought to carry into the next paradox. Baryon acoustic oscillations are like cosmic fossils, echoes of a time when the universe was a roiling sea of plasma, so dense that sound waves could race through it at half the speed of light. Picture the cosmos in its infancy, just a few 100,000 years after the Big Bang, a superheated soup of protons, electrons, and light, constantly colliding and scattering. In this chaotic environment, gravity pulled matter together while radiation pressure pushed it apart, creating rhythmic ripples, sound waves, that propagated outward like the rings from a stone dropped in a pond. But unlike water, this primordial plasma had a critical quirk. When the universe cooled enough for atoms to form, suddenly light could travel freely, and those ripples froze in place, etched into the distribution of matter like grooves in a cosmic record. Today, those frozen ripples manifest as a subtle preference in the spacing of galaxies. When astronomers map the universe on the largest scales, they find galaxies are slightly more likely to be separated by about 500 million light-years, a distance that corresponds to how far those ancient sound waves could travel before the plasma cooled. This pattern isn't random. It's a direct snapshot of the universe's acoustic adolescence, a relic so precise it can be used as a standard ruler to measure cosmic distances across billions of years. By comparing the apparent size of these oscillations at different epochs, scientists can track how the universe's expansion has accelerated or decelerated under the influence of dark energy and gravity. It's like finding a series of identical tuning forks scattered across time, each one vibrating at a frequency that reveals how much space has stretched since the moment it was forged. The real power of Baryon acoustic oscillations lies in their universality. Unlike supernova or other cosmic yardsticks, which depend on the brightness or behavior of individual objects, BAOs are statistical. They emerge from the collective arrangement of galaxies across vast volumes of space. This makes them incredibly robust, immune to the quirks of stellar evolution or the dimming effects of interstellar dust. Surveys like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument have mapped millions of galaxies to trace these oscillations, revealing not just the universe's expansion history, but also the tug of war between dark energy's push and dark matter's pull. The resulting 3D maps are like sonograms of the cosmos, showing how its structure has grown and shifted over eons. But BAOs aren't just measuring sticks, they're time capsules. The exact shape and scale of these oscillations encode details about the early universe's composition, from the amount of ordinary matter to the density of dark energy. Tiny deviations in the pattern could even hint at physics beyond the standard model, like unknown particles or extra dimensions. Future telescopes, like the European Space Agency's Euclid mission, will refine these measurements to unprecedented precision, potentially uncovering secrets about inflation, neutrinos, or the nature of gravity itself. What's astonishing is how these oscillations bridge the cosmic and the quantum. The initial ripples were born from quantum fluctuations during inflation, microscopic wrinkles stretched to cosmic proportions, and then amplified by the interplay of matter and radiation. In a very real sense, when we study BAOs, we're seeing quantum mechanics writ large across the sky, a reminder that the universe's grandest structures grew from its tiniest beginnings. And just as a single note can reveal the shape of the instrument that produced it, these frozen sound waves may yet reveal the shape of reality itself. Exotic matter sounds like something from a physicist's wish list, particles so strange they defy the ordinary rules of reality. But these hypothetical oddballs, like actions and magnetic monopoles, might be more than just theoretical curiosities. They could be the universe's ultimate time capsules, preserving information from the earliest moments of existence in ways no ordinary matter ever could. Picture a particle so aloof it barely notices the rest of the cosmos, drifting through galaxies and black holes without a scratch, carrying secrets from a time before stars. That's the promise of exotic matter, pristine messengers from the past, untouched by the chaos of cosmic evolution. Take actions, for example. These hypothetical particles were first dreamed up to solve a puzzle in quantum physics, but they've since become prime candidates for dark matter. What makes them extraordinary isn't just their invisibility, it's their near-perfect resilience. Unlike protons or electrons, which constantly interact with light and other particles, actions barely acknowledge the universe around them. If they formed in the early cosmos, they could still be cruising through space today, their properties frozen in time like insects trapped in amber. Their spin, their energy, even their quantum states might hold unaltered records of the universe's first microseconds, before quarks locked into protons or gravity carved the cosmos into structure. Detecting them wouldn't just reveal dark matter's identity, it could hand us a perfectly preserved snapshot of creation itself. Then there are magnetic monopoles, theoretical particles that carry just one magnetic pole, north or south, instead of the paired poles we're used to. If they exist, they'd be relics of a far more symmetrical universe, born when the fundamental forces were still unified. Some theories suggest they'd be incredibly massive, possibly even primordial, forming defects in spacetime as the cosmos cooled. These cosmic fossils would be so stable that nothing, not the heat of stars, not the pull of black holes, could destroy them. A single monopole passing through a detector today might carry imprints of the universe's first phase transitions, moments when the laws of physics themselves were still settling into their current form. It's like finding a scroll from a lost civilization, written in a language we're only beginning to decipher. What makes these particles such perfect time capsules is their stubborn refusal to interact. Ordinary matter is constantly buffeted by radiation, gravity, and collisions, erasing delicate quantum information over time. But exotic particles, by their very nature, sidestep this noise. An action born in the Big Bang's aftermath wouldn't just avoid collisions, it might never have bumped into another particle in its entire existence. That means its quantum state, its energy, even its trajectory could be unchanged since the dawn of time, offering a direct line to conditions we've only ever modeled in equations. The hunt for these elusive particles is already underway. Experiments like ADMS use powerful magnetic fields to coax actions into revealing themselves, while monopole searches scan ancient minerals and even moon rocks for traces of these magnetic anomalies. The challenge is immense. We're looking for needles in a cosmic haystack, particles that might pass through Earth once a century, but the payoff could rewrite physics. If we catch even one, it wouldn't just confirm a theory, it'd hand us a key to the universe's locked archives, a way to read chapters of cosmic history we thought were lost forever. And that's the real magic here. Exotic matter isn't just a scientific frontier. It's a glimpse into a universe that remembers itself in ways we're only starting to imagine. Whether through actions whispering quantum secrets or monopoles stamped with primordial magnetism, these particles remind us that the past isn't always gone. Sometimes it's just hiding in plain sight, waiting for the right tool, the right idea, the right moment to step back into the light. Quantum decoherence is like the universe's slow fade to static, a gradual unraveling of the delicate quantum states that encode the most fragile layers of cosmic memory. Picture a pristine snowflake landing on your palm. For a brief moment, its intricate structure holds perfect symmetry, every crystalline branch a testament to the exact conditions of its formation. But then warmth creeps in and the delicate patterns melt into formless droplets. That's decoherence in action, the inevitable process where quantum systems, once isolated and perfectly coherent, become entangled with their environment, blurring their quantum uniqueness into classical noise. In the cosmos, this phenomenon isn't just a curiosity, it's a silent editor, determining which quantum memories survive and which dissolve into oblivion. Consider Schrödinger's famous thought experiment, where a cat exists in a superposition of alive and dead states until observed. In reality, that superposition wouldn't last more than a fraction of a second. The instant the hypothetical cat interacts with air molecules, light, or even the vibrations of its own atoms, decoherence kicks in, collapsing the quantum weirdness into a single, definite outcome. Now scale this up to cosmic proportions. The early universe was a quantum playground, a place where particles existed in vast, entangled superpositions, their states interwoven like threads in a tapestry. But as the cosmos expanded and cooled, these quantum connections frayed under the relentless bombardment of radiation, gravity, and collisions. Decoherence didn't just happen, it shaped the universe's ability to remember its own infancy. Yet not all quantum memories fade equally. Some cosmic records seem stubbornly resistant to decoherence's erasure. Take quantum entanglement, for example. Particles born together in the fiery chaos of the Big Bang can remain eerily linked across billions of light years, their spins or polarities mirroring one another instantaneously, as if no time or distance had passed. How do these fragile connections survive while others crumble? The answer might lie in isolation, in the near-perfect vacuum of interstellar space, far from the disruptive buzz of matter and energy. Entangled particles can avoid the environmental interactions that trigger decoherence. It's like two people whispering in a soundproof room. The outside world never drowns out their conversation. Black holes add another layer of intrigue. According to the holographic principle, information swallowed by a black hole isn't destroyed but encoded on its event horizon. But here's the twist. The extreme gravity near a black hole's edge creates a phenomenon called quantum scrambling, where information is chaotically mixed but not necessarily lost. Some theories suggest this scrambling could actually delay decoherence, preserving quantum states in a twisted, encrypted form that leaks back out via Hawking radiation. It's as if the black hole is a cosmic cryptographer, taking fragile quantum memories and stamping them into a more durable, if enigmatic, format. The implications for cosmic archaeology are profound. If decoherence erases certain quantum signatures while sparing others, it acts as a filter, a cosmic curator deciding which chapters of history remain legible. The cosmic microwave background, for instance, carries faint polarization patterns that might hold traces of primordial gravitational waves. But decoherence over 13.8 billion years has likely blurred the finer details, like a photograph left out in the rain. On the other hand, quantum fluctuations frozen into the large-scale structure of the universe, the distribution of galaxies and voids, are so macroscopic that decoherence couldn't touch them. They're the universe's etchings carved into spacetime itself. This duality raises a tantalizing question. Could we reverse engineer decoherence to recover lost quantum memories? In labs, scientists are already experimenting with quantum error correction, using intricate algorithms to reconstruct information from decohered systems. If scaled up, similar techniques might one day let us deblur the universe's earliest quantum states, teasing out signals from the noise. Imagine tuning into the cosmic equivalent of a corrupted hard drive and recovering snippets of the Big Bang's first quantum whispers, not as simulations, but as actual data preserved against all odds. Decoherence isn't just a technical hurdle, it's a narrative force. It tells us that the universe's memory isn't a perfect archive but a palimpsest, where some stories are written in indelible ink and others in vanishing ink. As we learn to read between the lines, we might discover that the past isn't just what's preserved, it's also what's been lost, and why. And in that interplay of survival and erasure, we could find clues to the deepest mysteries of time, reality, and the quantum fabric that weaves them together. Quantum mechanics has always flirted with the idea that observation isn't just passive, it's participatory, somehow shaping the reality it measures. Think of the classic double-slit experiment, where particles behave as waves until someone watches, then suddenly choose to act like particles. This bizarre phenomenon suggests that consciousness, the act of observation, might be tangled up with the fabric of reality itself. Now stretch that idea to cosmic scales. If a conscious observer can collapse quantum probabilities in a lab, could the collective observation of the universe by stars, planets, or even intelligent life leave imprints on spacetime itself? It's a dizzying thought. That memory might not just be stored in the cosmos, but actively shaped by the minds that perceive it. This isn't just philosophical musing, it's grounded in interpretations like the von Neumann-Wigner hypothesis, which posits that consciousness causes the collapse of quantum wave functions. In this view, reality remains in a haze of possibilities until an observer crystallizes it into definite states. Apply this to cosmic memory, and suddenly black holes, quantum foam, or even dark matter distributions might not just record history, they could be co-authored by the act of observation. Imagine a black hole's event horizon not just preserving information like a hard drive, but dynamically updating its data based on what's being observed elsewhere in the universe. The implications rewrite the rules. Memory isn't fixed but fluid, a dialogue between the cosmos and its inhabitants. But how could consciousness, something so seemingly small and local, influence something as vast as space-time? The answer might lie in scale. Consciousness doesn't have to be human or even biological. Some panpsychist theories propose that all matter, from atoms to galaxies, has a rudimentary form of experience. In this framework, a star's nuclear processes or a planet's magnetic fields could be primitive observers, continuously collapsing quantum states in their vicinity. Over billions of years, these micro-observations might accumulate into macro patterns, subtly sculpting the universe's memory architecture. It's as if the cosmos is a self-referential loop, observing itself into existence while etching its own history. The most radical extension of this idea comes from theories like participatory universe models, where reality is a collaborative construction between observers and the observed. In such a cosmos, memory isn't a static record but a living process, evolving as new observers, whether civilizations or quantum systems, interact with it. A supernova's light, for instance, might not just carry information about the explosion. It could encode how countless observers, from interstellar dust to telescopes, have processed that event over time. This turns cosmic memory into something akin to a shared dream, where every participant, conscious or otherwise, leaves traces in the narrative. Critics argue this veers into metaphysics, but intriguingly, physics might be catching up. Quantum Darwinism, a modern interpretation, suggests that certain quantum states survive decoherence precisely because they're repeatedly observed by the environment. Apply this to the universe's structure, and the galaxies we see might be the preferred states that endured because they were most observed not just by us, but by the cosmic web itself. This subtly mirrors how human memories stabilize. Frequently recalled experiences become entrenched, while forgotten ones fade. The universe, in this light, might remember what it's paid attention to. The paradox, of course, is the chicken and egg problem. Did observers emerge because the universe remembered itself a certain way, or did the universe's memory form because observers shaped it? Perhaps the answer lies in between, a feedback loop where observation and memory co-evolve, each refining the other across billions of years. If so, then searching for cosmic memory isn't just about decoding spacetime's imprints, it's about understanding our own role in the story. After all, if consciousness truly shapes reality, then every time we gaze at the stars, we're not just witnesses to history, we're its collaborators. We're standing on the brink of a revolution in cosmic archaeology, not with shovels and brushes, but with quantum circuits and laser interferometers. Imagine a future where we don't just study the universe's history through distant starlight, but decode it directly from the fabric of spacetime itself. Quantum computers, with their ability to simulate quantum gravity or model the behavior of entangled particles across billions of years, could act as time machines in silicon, reconstructing events we once thought were lost forever. These machines wouldn't just crunch numbers, they'd unravel the universe's deepest encryption, teasing out patterns from the noise of quantum fluctuations or the faint echoes of black hole collisions. It's like handing a linguist a stack of ancient, fragmented scrolls, only these scrolls are written in the language of spacetime, and the ink is made of gravitational waves. Speaking of gravitational waves, the next generation of detectors is poised to turn the cosmos into an open book. The Laser Interferometer Space Antenna, or LISA, isn't just an upgrade to current ground-based observatories, it's a paradigm shift. Slated for the 2030s, this trio of spacecraft will float millions of miles apart, connected by lasers precise enough to detect ripples in spacetime 1,000 times fainter than what LIGO can catch. But here's the game changer. LISA won't just listen for the crashes of black holes. It'll tune into the universe's background hum, the steady drone of countless binary white dwarfs, the whispers of primordial black holes, even the faint tremors from cosmic strings if they exist. This isn't just astronomy, it's acoustics on a galactic scale, with spacetime itself as the instrument. Then there's the explosive potential of next-gen telescopes. The James Webb Space Telescope gave us a taste of what's possible, peering back to the universe's first galaxies. But projects like the 30-meter telescope or the European Extremely Large Telescope will go further, mapping the chemical fingerprints of exoplanet atmospheres with such precision that we could detect signs of life, or even more tantalizing, anomalies that hint at physics beyond our current understanding. Imagine spotting a star system with elements that shouldn't exist, relics of a previous cosmic cycle or evidence of exotic matter. These telescopes won't just observe the universe, they'll interrogate it, demanding answers to questions we haven't even thought to ask yet. But the real dark horse in this race might be neutrino observatories. These ghostly particles, as we've seen, are near-perfect messengers, but next-gen detectors like the Deep Underground Neutrino Experiment or the proposed Pacific Ocean Neutrino Experiment aim to catch them with unprecedented precision. By analyzing the cosmic neutrino background, the faint afterglow of the Big Bang's first second, we could glimpse a snapshot of the universe before protons even formed. It's like finding a pristine ice core from the dawn of time, its layers untouched by the chaos that came after. What ties all these technologies together is their ability to cross-reference data in ways previously unimaginable. A gravitational wave signal matched with a neutrino burst and a peculiar gamma-ray flash could reveal the inner workings of a supernova or the birth cries of a black hole. Quantum simulations might help us interpret these signals, testing theories of holography or quantum gravity against real observations for the first time. This isn't just incremental progress, it's the dawn of multimodal cosmic forensics, where every wavelength, every particle, every ripple in space-time becomes a clue in the greatest detective story of all. And the most exciting part, we're not just building tools to observe the universe, we're building tools to converse with it, to ask questions and just maybe hear its replies. The universe has been keeping a diary for 13.8 billion years. With these technologies, we're finally learning to read its handwriting. The ability to rewrite cosmic memory sounds like the ultimate power until you realize it's also the ultimate responsibility. Imagine holding a cosmic eraser, one that could scrub away the universe's imprints like chalk from a blackboard. On one hand, this might let us correct catastrophic errors, perhaps smoothing out space-time ripples from a black hole collision before they devastate a distant star system. But on the other, what if deleting those ripples accidentally unravels the very fabric of causality? Those gravitational waves aren't just echoes, they're threads in the tapestry of time, connecting events across billions of years. Erase one, and you might sever a link essential to the universe's coherence, like pulling a single thread from a sweater and watching the entire garment unravel. This isn't just theoretical. In quantum physics, the butterfly effect takes on a terrifying new dimension. Tiny changes to entangled particles can cascade across space-time, potentially rewriting history in ways we can't predict. Consider the cosmic microwave background, those faint temperature variations that seeded galaxies. If we somehow corrected these primordial fluctuations, thinking we're optimizing the universe's structure, we might inadvertently erase the conditions that made life possible. It's like editing the first chapter of a novel, only to realize you've deleted the protagonist's birth. The universe's memory isn't just a record. It's the foundation of everything that follows. Then there's the philosophical weight of playing timekeeper. If we alter spacetime's archives, who decides what stays and what goes? Would we prioritize preserving the birth of stars over the quiet death of a comet? And what if erasing evidence of past cosmic violence like gamma-ray bursts or supernova robs future civilizations of warnings about existential threats? History, even cosmic history, isn't just about facts, it's about lessons. A black hole's merger might encode critical clues about gravity's nature. Tampering with its aftermath could blind us to breakthroughs waiting in those gravitational waves. The stakes grow even higher when we consider multiverse theories. If our universe is one of many, its memory might not be self-contained. Editing our timeline could ripple into others, like shouting into a cave and hearing echoes from tunnels you never knew existed. Some models suggest that quantum entanglement could span parallel realities, meaning a change here might rewrite there, too. The ethical dilemma expands from should we to do we have the right, especially if other conscious beings inhabit those branches of reality. Yet the most haunting question isn't about capability, but intent. Humanity's track record with power isn't flawless. We've polluted oceans, melted ice caps, and driven species to extinction, all while knowing the consequences. If we can't steward a single planet responsibly, how can we trust ourselves with the universe's memory? The irony is crushing. To manipulate cosmic history, we'd need wisdom far beyond our current maturity. Perhaps the greatest safeguard isn't technological but moral, a recognition that some mysteries shouldn't be solved, some archives shouldn't be opened, not because we can't, but because we shouldn't. This isn't a call to abandon research. Understanding cosmic memory is vital. It's the difference between reading a book and burning it. But as we stand on the threshold of decoding spacetime's deepest secrets, we do well to remember, knowledge isn't just about what we can change, but what we must preserve. The universe has kept its own records for billions of years without our help. Our role might not be to rewrite them, but to listen, and to humbly accept that some stories are bigger than the hand that holds the pen. The universe isn't just a backdrop for cosmic events, it's a meticulous archivist, etching every collision, explosion, and whisper of quantum fluctuation into the very fabric of reality. Think of spacetime not as an empty stage, but as a dynamic, self-referential canvas where every brushstroke leaves an indelible mark. Black holes encode information on their event horizons like celestial hard drives. Quantum entanglement weaves a web of interconnected memories across billions of light years. Even the vacuum of space itself crackles with latent energy, preserving fluctuations from the universe's first moments. This isn't science fiction, it's the cutting edge of cosmology, revealing a cosmos that doesn't just unfold, but remembers. Consider the audacity of this idea. The past isn't lost. It's folded into the geometry of the present, waiting to be decoded. Gravitational waves ripple through spacetime long after the black holes that birthed them have merged, carrying echoes of ancient violence. The cosmic microwave background, that faint afterglow of the Big Bang, isn't just radiation, it's a fossilized snapshot of the universe's infancy. Its subtle temperature variations encoding the seeds of galaxies yet to form. Even particles as elusive as neutrinos, streaming uninterrupted through the cosmos, act as silent couriers, delivering messages from stellar explosions that occurred before Earth existed. But the most profound implication isn't just that the universe stores information, it's that this memory might be active, shaping the future as much as it records the past. The holographic principle suggests that our three-dimensional reality could be a projection of data stored on a distant two-dimensional boundary, blurring the line between memory and existence. Quantum foam, that turbulent sea of virtual particles at spacetime's smallest scales, might retain imprints of pre-Big Bang conditions like subatomic scars. And dark matter, invisible yet omnipresent, could be the universe's ultimate historian, its distribution mapping every galactic collision and merger over billions of years. As we peer deeper into this cosmic archive, we're not just uncovering history, we're redefining what history means. Time isn't a linear sequence of erased moments. It's a layered tapestry, with every event interwoven through gravity, quantum entanglement, and entropy. The arrow of time itself might be an emergent property of how information spreads and settles, like ink diffusing in water. This shifts our role from passive observers to active interpreters, learning to read a language written in gravitational waves, quantum spins, and the faint whispers of particles long gone. The tools to decode this language are already in our hands. Gravitational wave detectors tune into spacetime's vibrations like cosmic stethoscopes. Quantum computers simulate conditions at the birth of the universe, teasing apart entangled states that might hold clues to the past. Telescopes map the large-scale structure of the cosmos, tracing patterns that reveal how dark energy and dark matter have sculpted reality over eons. Each breakthrough peels back another layer, showing us that the universe's memory isn't just a record, it's a dialogue. an ongoing conversation between the laws of physics and the events they govern. So what happens when we finally learn to read this cosmic library in full? We might uncover answers to questions we've barely dared to ask. Did time have a beginning, or is the Big Bang just one chapter in an infinite cycle? Are there universes beyond our own, their histories faintly imprinted on ours through gravitational leaks or quantum entanglement? Could space-time itself be a kind of neural network, processing and preserving information in ways that mimic consciousness? The possibilities stretch as far as the cosmos itself. This isn't just about satisfying curiosity, it's about understanding our place in a universe that remembers itself. We're not just inhabitants of space-time, we're participants in its story, our own lives fleeting notes in a symphony that's been playing for billions of years. And as we learn to listen, we might discover that the universe's greatest secret isn't how it began, but how it remembers and what it's trying to tell us. The next time you look up at the night sky, remember, you're not just seeing stars, you're gazing at a living archive, its pages written in light, gravity, and the silent, enduring language of time. What do you think? Could the universe's memory hold clues to our deepest origins, or even our destiny? Let's keep the conversation going in the comments, and if you've enjoyed this journey through the cosmos, hit subscribe so you don't miss our next exploration of the universe's grandest mysteries. Until then, keep looking up. You never know what secrets the stars might